Yes, so hello everyone, good morning. So this is in this video we're going to solve paper 1 2022 linear algebra solution, right? So in the previous two videos we have solved 2024 solutions and 2023 solutions of linear algebra. So in this video we will solve 2022 solution, right? So if you haven't watched those two videos, I strongly recommend you to watch those two videos and then you watch this video, right? Okay. So again, 2022 linear algebra has 5 questions and it carries 70 marks, right? So again, as I said earlier, that scoring 70 marks in linear algebra is very easy, right? Provided if you know all the concepts very well, right? Okay. So we'll start our first problem. So we will prove this. So it's a proving problem. Prove that any set of n linearly independent vectors in a vector space V of dimension n constitutes a basis for E, basis for V, right? Okay. So when a set is basis, we say a set S is a basis for a vector space V if that set S is linearly independent and that set S should span the vector space. That is, linear span of that set is equal to V. So in order to prove a set is a basis for a vector space, you need to prove two things, that set S is linearly independent and L of S is equal to V. Linear span of S is V. Now what this theorem states is, for a finite dimensional vector space V of dimension n, if a set is linearly independent, automatically it will be a basis. That means we need to prove it spans the vector space. Already it is linearly independent. Now we need to prove that this linearly independent set spans the vector space. Then we can prove that it is a basis and this theorem will be proved, right? So we'll start doing this. Uh, so we'll start proof. So prove that any set of n linearly independent vectors in a vector space of dimension constitute a basis for E. So before that, you have to understand one note, right? So you have to understand one note. So actually, this note is a theorem. Just a minute. Just a minute. Okay. This note is a theorem that we'll be using this to prove this theorem. So since it is a 10 mark, you just code this as a note, right? So let V be a let V be a vector space. Let V be a vector space. Uh, let V be a finite dimensional vector space. Let V be a finite dimensional vector space. Finite dimensional vector space. Vector space over a field F of dimension n. Of dimension n. Of dimension n, right? So let V be a finite dimensional vector space over a field F of dimension n. So let S is equal to, V1, V2 and so on up to Vn. Everything is clear, right? Audio and video. Yes, okay. So let S is equal to V1, V2, V3, Vn, V a set of linearly independent vectors, right? So we have n linearly independent vectors here for this vector space of dimension n. Then any set, any set in V, how I can quote, then any set in V which has more than n vectors, which has more than n vectors. Already this set n is linearly independent. Suppose then any set in V which has more than more than n vectors, more than n vectors is linearly dependent. Yes or no? Is linearly dependent. So if you know all the basics, then this note is very easy to understand for you, right? more than n vectors is linearly dependent. See, already we have n linearly independent vectors for a vector space of dimension n. Suppose if your set has more than n vectors means, then among those vectors some has to be linearly dependent. Yes or no? Yes. So make a note of this. So we will prove this theorem now. Proof. So prove that any set of n linearly independent vectors of dimension n constitute a basis for V. So let S is equal to V1, V2, V3 and so on up to Vn be a set of linearly independent vectors in V. Right? So we have a set S. Now we need to prove this set is a basis. Already this set is linearly independent. Now it is enough to prove linear span of S is V, right? A set will be a basis if that set is linearly independent and the L of S is equal to V. That is linear span of S is V. Already the set is linearly independent. If I prove L of S is equal to V, then this S is a basis, right? Okay. So we need to prove L of S is equal to V. So whenever you need to prove the equality, what we will prove? That is we prove that this V is contained in L of S and L of S is contained in V, right? V is contained in L of S and this L of S is contained in V. If I prove this, V is contained in L of S contained in V, that means V is equal to L of S. This is how we will prove in mathematics, right? Whenever you have to prove equality, you say this is contained in this and this is contained in this. As a result, both will be equal. Okay, so we will prove this. Now, first what we will do is we will prove that V belongs to L of S. This V belongs to L of S. What I can say, let us take what I can do is let us take an element V in S, right? Let us take an element V in S. I think there is some internet issue. I think video is clear. I think video is clear, right? Okay, so let us take an element B in B, right? You take one element B in B, you say that this B is also in L of S. So we'll prove this B is contained in L of S. So first we'll prove B is contained in L of S. Now you take an element B in B, right? You say that this B is also in L of S. Okay. Now we can say that V1, V2, V3 and so on up to Vn, comma V is linearly dependent. Yes or no? Is linearly dependent. Why? Because already we have n linearly independent elements. I'm taking an element V in V and I'm adding that V to the set of n linearly independent vectors, right? Then this set is linearly dependent by note. Already we have n linearly independent vectors. I'm taking one vector V in V and this set will be linearly dependent. Yes or no? Now by definition of linearly dependent, this set is linearly dependent means, what is the definition of linearly dependent? There exists at least some non-zero scalar. There exists some non-zero scalars such that alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 and so on up to alpha n vn plus alpha v is equal to 0. These are just definition of linearly independent vectors, right? Linearly independent means all scalar has to be 0. Linearly dependent means there exists at least one non-zero scalar such that this linear combination is 0, right? That is all alpha I is not equal to 0. This is the definition of linearly dependent vectors, right? Okay. So there exists some non-zero scalars such that alpha 1 v1, alpha 2 v2, alpha 3 v3 and so on up to alpha v is equal to 0. Not all not all alpha is 0, or we can say we can do like this, not all alpha I is equal to 0. There exists some non-zero scalars. Now we already know that now we already know now we already know the set v1, v2 and so on up to vn. This set is linearly independent, right? That means alpha 1 v1, alpha 2 v2 and so on up to alpha n vn is equal to 0. This means all alpha i's are 0. Yes or no? By definition of linearly independent. Assuming that everyone knows the basics of linear algebra, right? So alpha 1 v1, alpha 2 v2 and so on up to alpha n vn is equal to 0. All alpha i's are 0 because the set is linearly independent. Right? There exists if this linear combination is 0 means all scalars has to be 0 for definition of linearly independent. Now let us call this as some star. Right? Call this as some star. Now the star becomes right. Now star becomes, so what star says alpha 1 v1, alpha 1 v1, alpha 2 v2 and so on up to alpha n vn plus alpha v is equal to 0. So this thing is 0, right? By this, so we have 0 plus alpha v is equal to 0, right? See, here not all alpha are 0, right? Here not all alpha are 0. So this all these alphas are 0. So that means, can I say this implies this alpha is not equal to 0? Yes or no? All these alphas are 0. That is alpha is equal to 0. That is alpha 1, alpha 2 and so on up to alpha n. All these are 0. But by this star, this set is linearly independent. All these cannot be 0. That is alpha 1, alpha 2, alpha n up to alpha v. All cannot be 0 by definition of linearly dependent. Now we know that these alpha 1, alpha 2, alpha 3 and so on up to alpha n are 0. That means this alpha should not be 0. Is this clear? Right? Is this clear? Here not all alpha are 0. Right? Here not, let us say instead of all alpha, let us say here not all scalars are 0. Not all scalars are 0. But these scalars are 0. That means this scalar should be non-zero. So that means alpha is not equal to 0. So therefore, from star we have alpha 1 v1, alpha 2 v2 and so on up to alpha n vn plus alpha v is equal to 0. This implies, can I write alpha v is equal to minus of alpha 1 v1, alpha 2 v2 and so on up to alpha n vn, because this scalar is non-zero scalar. This alpha is non-zero, right? That means, can I write this b to be minus 1 by alpha 1 v1, alpha 2 v2 and so on up to alpha n vn? I do like this because this alpha is not equal to 0. Yes or no? This alpha is not equal to 0. That means I can bring this alpha here. If alpha is equal to 0, it will be undefined, right? It will be 1 by 0. See, actually, 1 minus 1 by alpha 1 into b. What is this actually? Can I say this b belongs to L of S. What is linear span of S? V is S is this. Then what about L of S? What about L of S? Yes, L of S consists of all linear combination of this set of vectors, right? So L of S consists of some alpha 1 V1, alpha 2 V2, and so on up to alpha n Vn. Right? Alpha 1, alpha 2, alpha 3, and so on up to alpha n are some scalars, right? This is also L of S, right? So if you multiply this inside, some minus alpha 1 by alpha is some scalar, that's it. Right? Again, minus alpha 2 by alpha, some scalar. So we are expressing this B as a linear combination of, that is B can be expressed as a linear combination of V1, V2, and so on up to Vn. That means what? B belongs to L of S. So we have proved the first part. So B belongs to L of S. That means where we have taken V. We have taken a vector, arbitrary vector V from small capital V. That means V is contained in L of S. Right? Call this as A. Now we'll prove the second part. Now we'll prove the second part. We have proved V is contained in L of S. Now we need to prove L of S is contained in V. Right? Now we need to prove L of S is contained in V. That is very simple, right? L of S is contained in V is very simple. See, we have S is contained in V. Now S is contained in V. Yes or no? V consists of all those vectors. S consists of all those linearly independent vectors in V. That means obviously S is contained in V. If S is contained in V, can I say L of S is contained in can I say L of S is contained in V? Right? Very simple. If S is contained in V, can I say L of S is contained in V? Right? This is very easy to prove. This implies L of S is contained in V. Because S consists of all those linearly independent vectors. Linear combination of vectors is also in V only because it is subspace, right? So therefore level is contained in V. So from A and B, V is equal to L of S. That means this set L of S is equal to V. Sorry, yes, L of S is equal to V. That means our set S, which is linearly independent vectors, spans our vector space capital V. That's it. So NC proof. So very simple proof. So we need to prove that for a finite dimensional vector space, V of dimension n, linear independent set alone guarantees that it is a basis. If a set is linearly independent, we need to prove automatically it spans our vector space. So what we did is we have constructed a set S, which is linearly independent set. Now I need to prove this L of S is equal to V. That is, we need to prove V is contained in L of S and L of S is contained in V. This is very easy part. You take one vector V in V. You say that that vector is also in L of S. You take one arbitrary vector V in V. You say that that vector V is also in L of S. So I'm taking a vector V in V. Now I'm adding this vector V to this set. That means this set is linearly independent now because already we have n linearly independent set for a vector space of dimension n, right? So that means this set is linearly dependent now. What is the definition of linearly dependent? This can be written as a linear combination. If this linear combination is 0, then at least one of the scalars should be non-zero. That means if this linear combination is 0, then not all alpha I is equal to 0. Not all alpha I is equal to 0 by definition of linear dependent. But this set is linearly independent. That means all these scalars here are 0. That is alpha 1, alpha 2, alpha 3, and so on up to alpha n are 0. That means alpha should not be 0 because here not all scalars are 0. But all these scalars are 0 up to this. That means this alpha should not be equal to 0. Right? So that means if alpha is not equal to 0, then I can write this vector as alpha is equal to minus of this thing. Then I can bring this alpha down because that alpha is not equal to 0, right? So that means this V can be expressed as a linear combination of V1, V2, Vn. That means this V is in L of S. I've taken a vector V in V. I've taken a vector small v in capital V. I have said that V is also in L of S. That means V belongs to L of S. That means V is contained in L of S. And obviously L of S is contained in V. So therefore V is equal to L of S. Right? Okay. So we'll move on to the next problem. Again, this is very easy problem. Let T is a map from R2 to R3 be a linear transformation such that T of 1, 0 is equal to 1, 2, 3 and T of 1, 1 is equal to minus 3, 2, 8. Find T of 2, 4. So very simple. First we will find a linear, let T is a linear map from R2 to R3, right? So first what we'll do is we will find a linear map T of x, y, right? We will find a map T of x, y. You have to find a map T of x, y, so that if you put x, y to be 1, 1, you have to get this vector. If you put x, y to be 1, 0, you have to get that vector. So how to find a linear map? Very simple, right? I've already explained in the PYQs. That is, let us take a vector x, y in domain. Then here you can see the basis vector are 1, 0 and 1, 1. Then this x, y can be written as some a times 1, 0 plus b times 1, 1. Right? Here our basis vectors are 1, 0 and 0, 1. Now what I have already said in the previous classes, you have to find the value of AB in terms of x and y. If it is a standard basis, we know that A is equal to x, B is equal to y. If you are watching my videos regularly, in the previous class I have said that you ought to write A and B in terms of x and y now. If this is a standard basis, then finding AB is easy. If not, lightly you have to adjust. Now we have x comma y is equal to this a comma 0 plus b comma b. That means can I say a plus b is equal to x, a plus b is equal to x, and then b is equal to y. So b is equal to y means what is a? A is equal to x minus b. So a is equal to x minus y. So you can see here that I have expressed ab in terms of x comma y. Now we have x comma y is equal to a into 1 comma 0 plus b into 1 comma 1. That yes or no? I can write any vector as a linear combination of the basis vectors. Now you take t on both sides. So t of x comma y is equal to a into t of 1 comma 0. I can take t outside, right? Sorry, I can take scalar outside. A into t of 1 comma 0 plus b into t of 1 comma 1. So what is a? What is a? A is x minus y. So x minus y, x minus y. What is t of 1 comma 0? So t of 1 comma 0 is 1 comma 2 comma 3 plus b times what is t of 1 comma 1? Minus 3 comma 2 comma 8. So that means we have t of x comma y is equal to, you just add the corresponding components. So we have x minus y minus 3y, x minus y into 1 minus 3y, comma 2x minus 2y, 2x minus 2y plus 2y, and then we have 3 times x comma y. So we have 3x minus 3y, and then we have plus 8y, right? So this is equal to x minus 4y, comma 2x, comma 3x plus 5y. This is a linear map. This is our required linear map. You can verify. You just put x is equal to 1, y is equal to 0, x is equal to 1, y is equal to 0, x is equal to 1. So 1, 2, 3. X is equal to 1, y is equal to 0. We will get 1, 2, 1, 2, 3. If you put 1, comma 1. So if you put 1, comma 1, 1 minus 4 minus 3, 1 which is 2, 3 into 5, sorry, 3 plus 5, 8. So our linear map is correct. Now we need to find t of 2, comma 4. We need to find t of 2, comma 4. So now t of 2 comma 4, so that means 2 minus 4 into 4, 2 into 2, 3 into 2 plus 5 into 4. So 2 minus 16, comma 4, comma 6 plus 20. So minus 14, comma 4, comma 26 is our required answer. See how easy it is. It is a 10 mark question. They are given T, we know that T is a linear operator, right? That linear operator takes 1 comma 0 to 1 comma 2 comma 3 and 1 comma 1 to minus 3 comma 2 comma 8. You find explicitly what that map is. How to find that map? You take any x comma y in the domain, then that can be expressed as a linear combination of basis vector. What is our basis vector here? 1 comma 0 and 1 comma 1. So that means you can write that x comma y is a linear combination of this AB are scalars, right? AB are scalars. Now you have to find AB in terms of xy. You just solve for AB in terms of x comma y. You apply t on both sides, you will get a linear map. Now they are asking t of 2 comma 4, right? Yes. We'll move on to the next problem. This is very simple. You just have to solve 12th standard level problem. That is the third question is our 12th standard problem. That is you have to solve this system of non-homogeneous system of linear equations, right? You have to solve non-homogeneous system of linear equation by Gaussian elimination method. We will do this problem now. Very simple. I do this is fast. So this is a which is a non-homogeneous system, which is a non-homogeneous system, right? So that is we have ax is equal to b. So what is a? A is 1, 2 and minus 1, 2, 3 and 5, minus 1, sorry. So minus 1, minus 3 and 8. And our vectors, unknown vectors are x1, x2, x3 equal to 2 comma 5 comma 1. So we will solve by Gaussian method. So we will find the augmented matrix a comma b. So we have 1, 2, minus 1 and 2, 2, 3, 5, 5, minus 1, minus 3, 8 and minus 1, right? So we'll reduce this to row echelon form. So we have R2 is transformed to R2 minus 2 times R1. R3 is transformed to R3 plus R1. So this becomes 1, 2, minus 1 and 2. You multiply 2 and then you subtract. You multiply 2 and then you subtract. So 3 minus 4 is minus 1. You multiply 2 and then you subtract. So 5 plus 2 is 7. You multiply 2 and then you subtract. So 5 minus 4 is 1. 5 minus 4 is 1. Now you just add R3 plus R1. Minus 1 plus 1 is 0. Minus 3 minus 3 plus 2 is minus 1. 8 minus 1 is 7. Minus 1 plus 2 is 1. Right? So this is not in row echelon form. So R3 is transformed to R3 plus R2. So this is equivalent to 1, 2, minus 1, 2, 0, 0, minus 1, 7, 1. This becomes 0, 0, 0, 0, right? You just add the, sorry, you have to subtract R3 minus R2. Now this is in row echelon form, right? So when a matrix is said to be in row echelon form, first row, first non-zero element, below the corresponding column, everything has to be 0. Yes. Second row, first non-zero element, below that corresponding column, everything has to be 0. Yes. Third row, there is no non-zero element. So this is in row echelon form. Now you just compare what is rank of A? Rank of A is 2, right? And what is rank of A comma B? See, if you go to our live section, there will be a playlist called how to solve a system of equations, right? I have already taught how to solve a homogeneous and non-homogeneous system. Just watch that if you haven't know to solve. So rank of A and rank of A comma B both are equal to 2. That means the system is consistent and has infinitely many solutions, right? The system is consistent, has infinitely many solutions and has infinitely many solutions. So how to find all those solutions? how to find all those solutions? You just have to use the idea of number of free variables, right? So how many free variables here? So number of free variables. Number of free variable is n minus rank of a. So n is total number of variables minus rank of a is 2. So we have one free variable here. So we have one free variable. So let us assume x3 to be equal to k. Right? Let us assume x3 to be equal to k. Now you write this back to ax equal to b form. You write again this back to ax equal to b form. So 0 minus 1 7 0 0 0 x1 x2 x3, and then the output vector now is 2 1 0. Now we have a system of equations, right? x1 plus 2x2 x1 plus 2x2 minus x3 equal to 0. X1 plus 2x2 minus x3 is equal to 0, minus x2 plus 7 times x3 is equal to 0. Now we know that x3 is equal to k by assumption. That means what is our x2 now? Call this as 1, call this as 2. So from 2, so minus x2 plus 7k is equal to 0. That means x2 is equal to 7k, right? And from 1, what is x1? x1 is equal to x3 minus 2x2. So x3 is k, x2 is 7k. So we have k minus 14k, so which is minus 13k, right? So therefore our solution is x1, x2, x3 is equal to, so x1 is minus 13k, x2 is 7k, and x3 is k. This k belongs to real number. If you vary k, you will have infinitely many solutions. For example, if you put you just put k is equal to when 1. What's our solution? Minus 13 comma 7 comma 1, right? You can see that minus 13 comma 7 comma 1 will satisfy this equation. Can we check it? So x1 is minus 13, x1 is minus 13, 2 times x2. So x2 is 7 minus x3 is 1. So what is 2 sevens are 14, 14 minus 1 is 13, minus 13 plus 13 is 0, and again minus x2. So minus x2 is minus 7, minus 7 plus 7 times x3. So minus 7 plus 7 is 0. So that means if you vary k, all these tuple will be a solution for our non-homogeneous system, right? So find all solutions to the following system of equations by row reduced method. Therefore, this has infinitely many solution. That solution is given by this set of vectors, right? Yes. So now we'll move on to Yoga Basha. What you have asked? How we can equate it to 0 in 1 and 2? Okay, okay, okay. I think I have made mistake. Sorry, sorry. Sorry, sorry, sorry. It is equal to 2, right? Okay, x1 plus 2x2. Sorry, x1 plus 2x2. Sorry, x1 plus 2x2 minus x3 equal to 2. And then we have minus x2 plus 7x3 minus x2 plus 7x3 is equal to 1. Okay, sorry for wasting your time. So let us put x3 to be equal to k. So that means minus x2 is equal to 1 minus 7x3. So 1 minus 7 times x3 is k. So that means x2 is equal to 7k minus 1, right? All this as 1, all this as 2. And from 1 we have x1 is equal to 2 plus x3 minus 2 times x2. So 2 plus x3 is k minus 2 times x2 is 7k minus 1. So 2 plus k minus 14k plus 2. So 4 minus 13k. right? So therefore the solution is x1 comma x2 comma x3 is equal to, so x1 is 4 minus 13k, x2 is 7k minus 1, and then this k, right? You can check this now. If k is equal to 1, if k is equal to 1, what do you will have? 4 minus 13. 4 minus 13 is minus 9. If k is equal to 1, 7 minus 1 is 6, 1. You see whether it satisfies or not. So minus 9 comma 6 comma 1. So this is minus 9 plus 2 times x2. x2 is 6 minus x3. Minus 7x3. That means 7k minus k plus 4 minus 13k in x2. What you will have? Yes, we have got this to be 2, right? So we have 12 minus 10 is 2, and also you can here also you can see minus x2. That means minus 6 plus 7, which is equal to 1. Therefore, this is our solution. This is our solution space, right? Sorry, I thought it is 0, 0, 0. Okay, we'll move on to the next problem. The solution space is given by 4 minus 13k, 7k minus 1, and k, right? Yes. So we'll move on to the next problem. Is it clear? Okay, so we'll move on to fourth problem now. Let the set P, right? Let the set P x comma y comma z, x minus y minus z is equal to 0, 2x minus y plus z is equal to 0 be collection of vectors of vector space R3 of R. Prove that P is a subspace of R3, and then we need to find the basis and dimension of P, right? Okay. You can see this x comma y comma z is a solution of this homogeneous system of linear equations. We know that solution of homogeneous system of linear equation always forms a subspace, right? Solution of homogeneous system always forms a subspace. Yes or no? That we already proved in our linear algebra lectures. Um, but no problem. We'll do again. What is the definition of subspace? What is the definition of subspace? We have a vector space V, and then we have a subset W of P. You take two elements U V. You take U comma V in W, right? You take alpha beta from the field F. Then what is the definition of subspace? Alpha U plus beta V belongs to V. Yes or no? Alpha U plus beta V belongs to V or W. V or W? W, right? How I can write V? Alpha U plus beta V belongs to W. This is a definition of subspace, right? You take UV in W, you take alpha beta from the field, then alpha U plus beta V is also in W, then I can say this W is a subspace. This is a definition of subspace, right? Necessary and sufficient condition for a set S to be a subspace of V. Okay. Now we'll do this. We need to prove that this set is a subspace. So we have a set P. So P consists of all those x comma y comma z such that uh, x minus y minus z is equal to 0. 2x minus y plus z is equal to 0. You can do by two things. One thing is you can show like the solution system, the solution space of homogeneous system is a subspace. You can prove that, or you can prove by definition. I'll prove by definition. Uh, so we have W to be all those vectors that satisfy these two equations, right? Okay. So we'll do this now. So let us take uv in w. So let us take here u and v both are vectors of R3. So let us take u to be some x1 comma x2 comma x3. That means this u, I'm taking this u in a p. Yes or no? Let us take. Uh, I'll write it more clearly. Let us call this to be some w, right? Let us call this to be some w so that it will be easy for you to visualize. Let us call this to be w. Now, what's the definition of a subspace? You take uv in w. So let us take an element u comma v in w. What is our w? W is p. So let us take u to be some x1 comma x2 comma x3. That means we have taken x2 x1 x2 x3 from the solution space. That means this vector will satisfy both the equations. That is x1 minus x2 minus x3 is equal to 0. And then we have 2x1 minus x2 plus x3 is equal to 0. And let's take b to be some y1 comma y2 comma y3. This implies this vector is in p. That means this vector will satisfy both the equation. So y1 minus y2 minus y3 is equal to 0. 2 times y1 minus y2 plus y3 is equal to 0. Now what you need to prove? To prove what I need to prove? Alpha u plus beta v is also in w. That means alpha u plus beta v also satisfy these two equations. That is what I need to prove. Now what is alpha u plus beta v? Alpha u plus beta v. So alpha times what is u? x1 comma x2 comma x3 plus beta times what is v? y1 comma y2 comma y3, right? Now this is alpha x1 plus beta y1, alpha x2 plus beta y2, alpha x3 plus beta y3. Now I need to prove that this set, that is this vector, satisfies both the equations. If I say this vector satisfies both the equation, can I say alpha u plus beta v belongs to w? That means it will be a subspace. Now I need to prove. Now we will see whether this vector satisfies these two equations or not. Now we will find x minus y minus z. Now what is alpha x1 plus beta y1? This is our x now. This is our y minus alpha x2 plus beta y2 minus x3 alpha x3 plus beta y3, right? This is equal to, can I write this as alpha x1 minus x2 minus x3, right, plus beta y1 minus y2 minus y3. Now this is 0, right? Because we know x1 minus x2 minus x3 is 0, 2x1 minus x2 minus x2 x1 minus x2 plus x3 is 0, because we have taken uv from the set, right? That means this uv will satisfy both the equations. So that means this vector satisfies the first equation. Also 2x, also 2x alpha x1 plus beta y1, 2x minus y, so minus y alpha x2 plus beta y2 minus plus z alpha x3 plus beta y3. So can I write this as alpha times 2x1 minus x2 plus x3 plus beta times 2y1 minus y2 plus y3. So this is alpha times 0 plus beta times 0. Yes or no? So that means this vector satisfies both the equation So this implies this vector is alpha u plus beta v. So alpha u plus beta v belongs to W. So that means our set W, which is P, is a subspace. So we have proved the first part. So very simple. You take two vectors in W. You say that alpha u plus beta v is also in W. So we'll approve the first part. Now we'll do a second part. Find the basis and dimension of P. So what is P here? P is our solution space of homogeneous system. So x comma y comma z, x minus y minus z is equal to 0. X minus y minus z is equal to 0. 2x minus y 2x minus y plus z is equal to 0. So we will find the dimension and basis. So we just find the solution space. So solution space, so this is nothing but our solution of this homogeneous system Ax equal to 0. So A is 1 minus 1 minus 1, 2 minus 1 1, 0 0 0, and then we have x comma y comma z equal to 0 comma 0 comma 0. So we'll form the augmented matrix A comma O. So 1 minus 1 minus 1 0. So 2 minus 1 1 0, 0 0 0 0, right? So we'll make a reduced row echelon form. So R2 is transformed to R2 minus 2 times R1. So this is equivalent to 1 minus 1 minus 1 0. So this will be 0. So minus 1 minus 2 times minus 1. So minus 1 plus 2, so which is equal to 1. And then we have 1 minus 2 into minus 1, so which is 3 here, 0. And then 0 0 0 0. This is in row echelon form, right? Which is in row echelon form. And then we have rank of A to be equal to 2, and the rank of A comma O is also equal to 2. That means the system is always consistent for homogeneous system, because trivial solution is always a solution. System is consistent and has infinitely many solutions, right? How to find all those solutions? You just make use of the idea of number of free variable. Now number of free variables is total variables minus rank of A. Total variable is 3 because you have x, y, z. Rank is 2. So we have one free variable. Now again, write this in equation format. So we have x minus y minus z is equal to 0. Then we have y plus 3z is equal to 0. So let us put z to be equal to k. We have one free variable. So that means y will be equal to minus 3k, and x will be equal to y plus z, which is minus 3 plus k, is equal to minus 2k. So that means our solution space x comma y comma z is given by minus 2k comma, what is y? Y is minus 3k comma k. So that means k times minus 2 comma minus 3 comma 1. So you can see our solution space is spanned by one vector, which is minus 2 comma, minus 3 comma 1. Our solution space is spanned by the one vector, which is minus 2 comma, which is minus 2 comma minus 3 comma plus 1, right? Minus 2 comma minus 3 comma plus 1. That means this is our basis, right? This is our basis. Basis need not be unique, right? This k belongs to a real number. So basis is given by minus 2 comma minus 3 comma 1, and the dimension is what? 1, right? Because what is dimension actually? Number of elements in the basis. So this one vector alone spans our solution space. So dimension is 1, and the basis is given by minus 2 comma minus 3 comma 1, right? One of the basis. For example, if you put k is equal to minus 1 by 2, or k is equal to plus 1 by 2, or you put k to be any real number, but this vector is spanned by this vector alone. This set is spanned by this vector. Any linear combination is also a solution, but this single vector alone is enough to span our entire vector space. and this single vector is linearly independent as well as it will span our solution space. So therefore, it is a basis and number of elements is one vector here. So we have dimension to be equal to 1 and basis is -2 comma -3 comma plus 1, right? Is it clear? So we'll move on to the last problem of today. Find a linear map T from R2 to R2 which rotates each vector of R2 by an angle theta, and also prove that for theta is equal to pi by 2, T has no real eigenvalues in R, right? So we'll prove the last problem. Is it clear up to now? Is it clear up to now? Okay. Okay. So find a linear map T that rotates each vector of R2 by an angle theta. Okay. So in 12th standard complex numbers, we have studied rotation theorem. And I recall rotation theorem in complex numbers. Okay. That's the idea for this. Find a linear map T. So we have a vector x comma y. Let us say it makes an angle alpha with the positive x-axis. Now we are rotating this vector by an angle theta, right? This will be a new coordinate which is x dash comma y dash. So let us say this length is r, right? Let us say this length is r. Then what about x comma y? What is the coordinate for x comma y? X is nothing but what? Cos alpha. Y is x is nothing but r times cos alpha. Y is r times sin alpha. Basic uh, components, right? Physics. So if this angle is alpha and if this distance is r, then this x length is x r times cos alpha. This is r times sin alpha, right? Now, if you are rotating by an angle theta, what will be our x dash and y dash? We are rotating only, so the magnitude will not change, right? If this is r, this is also r. So what about the new x dash y dash? It is nothing but r times what is the full angle? Theta plus alpha. So but this x dash y dash will be r times cos of theta plus alpha. Y dash will be r times sine of theta plus alpha. That is the coordinate for x dash y dash. This idea is clear. The coordinate for x comma y is r times cos alpha, r times sin alpha, and the coordinate for x dash y dash is r times cos of theta plus alpha, y dash is r times sin of theta plus alpha. This is clear. So this is what I'm going to write now. Whatever I've said, I'm going to write now. Right. So let us take x comma y belongs to R2, and let us say it makes an angle of alpha with positive x-axis. Then obviously, what is our x comma y? Let x comma y belongs to R2 of magnitude r, right? That is the length is r. Or else can I write like, because the precision is very important, max. Let us take a to be let us take some t to be x comma y of magnitude r, that is ot is equal to r, that is distance from o to t. Now can I write this x comma y as r times cos alpha comma r times sin alpha? So this is our new coordinate for x comma y in terms of polar form. Now what is x dash comma y dash? What is x dash comma y dash? R times cos of theta plus alpha, r times sin of theta plus alpha. Yes or no? Now x dash y dash be a coordinate after rotating by theta, after rotating x comma y by theta, then the new coordinate x dash comma y dash is given by r times cos of theta plus alpha, comma r times sin of theta plus alpha. Now what is this r times, what is cos a plus b? Cos a cos b. Is it clear, right? What is what is cos a plus b? Cos a cos b minus sin a sin b, right? So cos a cos b minus sin a sin b. What is sin a plus b? Sin a cos b plus cos a sin b. Cos a sin b. Now we'll multiply inside here. So this is r cos alpha cos theta minus r sin alpha sin theta, comma r cos alpha sin theta plus r sin alpha cos theta. Now already we know that r cos alpha is x. So this is x cos theta minus r cos alpha, r sin alpha. R sin alpha is y. So y sin theta, r cos alpha is x. So this is x sin theta and this is y cos theta. So this is the coordinate for x dash comma y dash. So therefore, if you want to rotate x comma y by an angle of theta, the new t, the new out t is given by t of x comma y is equal to t of, or else I'm using t to be for transformation, right? Let us call this as some a. So a is equal to r. So t of x comma y is given by x times cos theta minus y sin theta, comma x times sin theta plus y cos theta. So this is the transformation that makes x comma y, that rotates x comma y by an angle of theta, right? So t of x is the required, is the required linear transformation that maps. See, we have to put x comma y. That is, for example, if you want to rotate 1 comma 2 by an angle of 45 degree, what is the new vector? 1 cos 45 minus 2 sin 45. X comma y to be 1 comma 2 and angle to be, I'm taking 45. So 1 cos 45 minus 2 sin 45, comma 1 sin 45 plus 2 cos 45 is our new vector, transformed vector by rotating an angle of theta. Right? Okay, this is a linear transformation. Now this is a linear map. Also prove that for theta is equal to pi by 2, t has no real eigenvalue. Okay, if theta is equal to pi by 2, if theta is equal to pi by 2, what is our t of x comma y? What is our t of x comma y? r cos pi by 2, r cos pi by 2 minus y sin pi by 2, r cos pi by 2 minus y sin pi by 2, x sin pi by 2, x sin pi by 2 plus y cos pi by 2. So this is given by, so cos pi by 2 is 0, right? So this is given by minus y comma x. So t of x comma y is equal to minus y comma x. So this is a new map. New map if theta is equal to pi by 2. Now we need to prove this has no real eigenvalue. So we will find the corresponding matrix for this. We will find the corresponding matrix for this linear operator. So with respect to the standard basis, we will find the matrix of t. So what is t of 1 comma 0? It is 0 comma 1. And what is t of 0 comma 1? It is minus 1 comma 0. So the matrix of t with respect to the standard basis is given by 0, 1, minus 1 and 0. Now you find the characteristic polynomial for this 2 by 2 matrix. So what is the characteristic polynomial for 2 by 2 matrix? It is lambda square minus s1 lambda plus s2, where s1 is given by trace of a, trace of the matrix, and s2 is the determinant of that matrix. So we have lambda square minus, what is trace? Trace is 0, 0 lambda plus S2, S is determinant, so 0 minus of minus 1. So lambda square plus 1 is the characteristic equation or characteristic polynomial for our this linear operator. Now what is eigenvalue? The roots of this characteristic polynomial are the eigenvalue. What is the root for this? Lambda is equal to plus or minus I. That means it has no real eigenvalue, right? It has no real eigenvalue. It has no real eigenvalue. That's it, right? So we have completed our 2022 paper. So again, all problems are very easy. The only thing is you need the basic understanding and basic concepts of bases, dimensions, rank, nullity, eigenvalues, eigenvectors, right? Yes. The first problem is proving problem. We have proved this. Second is very simple. They have given t of 1 comma 0 as 1 comma 2 comma 3, t of 1 comma 1 as this. Find t of 2 comma 4. Very simple. And then third problem is just you have to solve the non-homogeneous system of linear equations. Actually, here I made two instead of 2 1 I put 0 0. So I wasted some 5 minutes time. Sorry for that. So and then we have proved that this is subspace. So by definition of subspace, we have proved this the first part. Second part is find the basis and dimension. So basis turns out to basis, dimension is 1. And then last term is we need to find a linear map that rotates x comma y by an angle theta. So this is a linear map that rotates x comma y by an angle of theta. Now we need to prove if theta is equal to pi by 2, t has no real eigenvalue. It has 15 marks, right? But how simple it is, right? All these are very standard questions. So no any tricky questions at all. All these are very standard questions. So the next class we will solve 2021 paper. Okay, so thank you. All the best. Bye.